So actually, before we get started, one thing for those of you, actually in either class, but specifically the Dell's class is what I was thinking of. I did post a practice exam that I wrote, I don't know, a year or so ago. It's obviously not going to be exactly like the exams that you're going to take, but you can find it in the modules. If you just scroll down to the bottom of the modules, there is practice exams, practice exam 1, and the solutions. I believe the solutions are not available until 7 p.m. just to give you all the chance to work on it without the temptation of looking at the answers, which I would always recommend doing for any kind of practice test, is to take it like a test and then try to look at the answers after. I would say that's very different than the practice problems the Dell provided for his class, right? That is definitely just to show you all, right? These practice problems over here, right? This is certainly longer than, or should be longer than, a reasonable test. So you shouldn't try to take these like they're an exam, although you should still try to do them without using outside resources until after you've attempted them. Okay. The plan for today is to talk about partial fractions to start, and then we'll do that for a bit. But before we do that, actually, there was a question about the last problem on the Dell's practice test, which is something we were talking about last class, which is integration by parts. So this is problem, let's write Co-17B. Today is April, what, 18th? Yeah, 18th. So we're given for this last problem in the Dell's practice exam that f prime of x is equal to e to the 3t cosine of t, 2t, which is an interesting way of asking this question, I feel like. So you're given this, interesting. I'm curious what he actually imagines here. And let me zoom in just a minute, because I feel like I am not seeing this super clearly on my screen. And I want to, interesting. I just want to see it. I guess I can't see it. I can't download it. Okay, fine. Can I zoom in? Maybe. Guess not. Yeah, that says, okay, it says given f prime of x, it says find f of x. Which feels kind of like, oh, sorry, you can't see what I'm writing at all. Apologies. You guys should say something. If you can't see what I'm writing, you should say something. So that's what the problem says. And what I would say, if I'm trying to find f of x, the way I'm going to write f of x, yeah, I feel like this x versus t here is actually a mistake. I don't feel like this was intentional or trying to like make you think about the fundamental thing calculus. I feel like he really just meant find the antiderivative unless something else is missing here. Here's what I think we're supposed to do. I'm going to write this as that f of x should just be the antiderivative of, I'm going to write it as e to the 3x cosine of 2x dx. I don't think he meant anything tricky by this. I really just think he accidentally used t instead of x in one place. I wouldn't start this unless he said something about it, well, over Canvas, because right, your next class is your test. Yeah.
Did you do I didn't figure out a change.
Sure, which one?
It's like the integral of sine ln of x.
Sure. Oh yeah, so actually that leads kind of into this. So yeah, we'll talk about this, and we might not finish that problem off, but we'll definitely talk about it. So I want to point out, whenever you have an integral like this, where it's e to a multiple of x times either cosine or sine of a multiple of x, there's a process for this, which is always the same. And the process is you have to do integration by parts twice. And then you're going to end up with the same integral that we started with. So let's do this one, and then we'll talk about the other one. And then we'll start talking about partial fractions, because we do have to cover partial fractions. So first, we're going to let u equal cosine of 2x. dv has to be the rest, which in this case is e to the 3x times dx. Our du is the derivative of cosine of 2x, which is negative sine of 2x dx. Our v is the antiderivative of e to the 3x, which is 1/3 e to the 3x. Question?
Isn't d negative 2 sine 2?
Oh, thank you. Yeah, I forgot the 2. Good call. So then we rewrite it, and we're going to get the integral, sorry, our u times our v. So it's going to be cosine of 2x times 1/3 e to the 3x minus the integral of our v times our du, which is 1/3 e to the 3x times -2 sine of 2x dx. Someone was asking me the other day about how, like, if you're doing integration by parts, do you have to change your limits of integration like we do in a u substitution when it's a definite integral? And the answer is no, because when you're using integration by parts, even though you're using a u and a dv, I want to point out we didn't actually change the variable we're using. We have an integral of x and we still have stuff with x's in it. So even though we use these other letters to help us get there, we're not actually changing the variable, unlike in a u substitution, where you are changing the variable. So those of you coming in, we're just working on problem 18 from Dell's practice exam, which is essentially to find the antiderivative of e to the 3x times cosine of 2x. So we've gotten to this stage here, and I personally, when I do this, I like to pull out the constant multiple. So I'm going to rewrite this as cosine of 2x. I'm going to put the 1/3 in front, actually. 1/3 cosine of 2x times e to the 3x. Minus a minus is going to be plus, and 1/3 times 2 is 2/3 integral of e to the 3x times sine of 2x dx. And then we're going to do another integration by parts. And I'm going to use a different color. We're going to let here for this integration by parts of this integral, we're going to let u equal sine of 2x. And we're going to be extra careful taking the derivative here. Actually, I should write dv first. And dv is going to be the rest, which is e to the 3x dx again. Our du is 2 times cosine of 2x, or cosine of 2x times the derivative of 2x dx. And our v, once again, is 1/3 e to the 3x. So when we write our uv minus the integral of v du, or as I like to say, our ultraviolet super v, we're going to get 2/3 times all of that uv minus the integral of v du. So we're going to get that this is equal to still 1/3 cosine of 2x times e to the 3x plus 2/3 times the entirety of u times v. So sine of 2x times 1/3 e to the 3x minus the integral of v du. So that's going to be 1/3 e to the 3x times 2 times cosine of 2x dx. And you can never seem to fit all this on one page. This never happens for me. So, okay, so I'm going to rewrite this. I'm going to distribute the 2/3 each of these terms, and I'm also going to write the left-hand side of my equation. So I'm going to remind myself that I'm finding the integral of e to the 3x cosine of 2x. So I have that the integral of e to the 3x times cosine of 2x dx is equal to 1/3 cosine of 2x e to the 3x plus, let's see, I have a 2/3 times a 1/3. That's going to be a 2/9 times sine of 2x times e to the 3x. And then a 2/3 times a 1/3 times a 2 is a 2/3 times a 2/3, which is a 4/9, and it is going to be a negative. So it's a negative 4/9 times the integral that we started with. The integral of e to the 3x times cosine of 2x. So this always happens with this type of integral, where it's e to the something times x times either sine of something times x or cosine of something times x. And what we do after this is we add this to both sides. I'm sorry, both sides here. So what we're going to do is we're going to take this and we're going to add the 4/9, the integral of e to the 3x cosine of 2x to both sides. What we're going to get is, well, if I have 1 of something plus 4/9 of something, 1 plus 4/9 is 9/9 plus 4/9, which is 13/9. So on the left-hand side here, I'm going to have 13/9 of my integral of e to the 3x times cosine of 2x dx equal to this stuff here. 1/3 cosine of 2x times e to the 3x plus 2/9 sine of 2x e to the 3x. And then finally, the last step is to multiply both sides by the reciprocal of that coefficient. So we're going to multiply both sides by 9/13, and we're going to get to the integral of e to the 3x times cosine of 2x dx is equal to 9/13 times all of that. 1/3 cosine of 2x e to the 3x plus 2/9 sine of 2x times e to the 3x plus c. You could distribute the 9/13, but there really isn't the need to do that. Kind of gross, but a typical kind of question. I don't know if this is typical for an exam. If I was going to ask this kind of question on an exam, I'd probably try to ask the easiest version of this, which is e to the x times either sine of x or cosine of x, so that these coefficients don't get so gnarly. But it's not an unreasonable exam question. So to the other question, oh sorry, are there questions about this before we move on to something similar but slightly different? Okay, so someone else asked about this problem, which we're not going to finish, but we will talk about how you would start. So if I want to find the integral of sine of the natural log of x dx. So this is going to end up being, oh, where did I get the 4/7? That's the 4/9, not a 4/7. So the 4/9 here, sorry, I know my 9s sometimes look like 7s. The 4/9 came from the fact that we had a 2/3 times a 1/3 times a 2. Yeah. Whoops. Okay. Right, let's get that back. Good. All right, so here, I don't see a whole lot of options. So I'm going to do the only thing that seems reasonable to me, which is to do a u substitution, which is letting u equal the natural log of x. Now, since I know that I'm going to end up having to do integration by parts after I make my u sub, I'm going to choose any letter other than u. So I want to save my letter u for when I have to do integration by parts. It's not required, but I feel like it makes my life easier. So I'm going to let t equal the only normal choice I would make for a u sub here, which is the natural log of x. And then I'm going to see that dt is 1/x dx, and that is not looking good for me. I would like for there to be a 1/x natural log of x, or sorry, 1/x dx, and there isn't. People deal with this in one of two ways, which both end up being the same. Here's the way that I think is easier. If I see that my dt is not helpful, or my du is not helpful, I go back and look at my u sub, and I solve for x. So solve this for x, in this case by raising both sides as powers of e. I'm going to write this as e to the t equal to e to the natural log of x, which just becomes e to the t equal to x. And then what I'm going to do with that is I'm going to differentiate both sides so that I can get what dx is equal to. So what's the derivative of e to the t? And the derivative of x is 1. But really what I'm going to write is that dx dt, the derivative of x with respect to t, is equal to the derivative of e to the t is e to the t. And then I'm going to move the dt over to the other side and say that e to the t times dt is equal to dx. Basically, whenever you're doing a u sub kind of thing and you differentiate both sides, just tack on the appropriate d whatever on each side. So if it's a side with t on it, multiply it by dt. If it's a side with x on it, take the derivative and multiply by dx. And then that's what we're going to end up plugging in for dx. Another way to get there, which is not my favorite, but also works, is you can say, oh, look, I know that from this work here, that x is equal to e to the t. So I could actually jam that right in there and say, I've got that dt is equal to 1/e to the t times dx, and then multiply both sides by e to the t to get the e to the t times dt is equal to dx. That'll also get you to the same thing. I find that less, I don't know, less typical. Like it just feels harder to make that work sometimes. Here it's not too bad. Sometimes you have to really kind of work with the algebra to make that work out. Yeah. So I knew that the dt wasn't helpful, or it's not helpful enough, because usually when we're trying to do a u sub, we want the derivative to exactly be in the integral. And it's not, right? I don't have a 1 over x times dx in my integral. So that's what I mean by not helpful. It's not what I would usually like. Like normally I'm hoping for like something like the integral of say like, you know, t squared times sine of t cubed dt. Then I'm going to let u equal t cubed and be happy because the derivative of t cubed is 3t squared. And I have a t squared in my integral. That's a more normal, nice u substitution. So here what's going to happen is you're going to end up rewriting this integral as the integral of, well, the dx becomes e to the t dt, and the sine of natural log of x becomes sine of t. And now we're back in the same sort of situation we were in for the previous problem, where we have the integral of e to the t times sine of t. You have to do that integral twice, get back the same thing you started with, and then add it over to the other side.
So we do everything, not, and then at the very, very end, once you have your answer, you plug in what t.
Right, so if you did all the work here, you would eventually get to the integral of sine of t times e to the t dt. Oh, should I remember the signs right? I believe it's going to be e to the t times sine of t minus e to the t times cosine of t. Let's see, you get e to the t times sine, yep, and then I think it's a 1/2 of all that. I'm pretty sure that's right. It might be slightly off. And then after you did all of that, you would then plug back in the fact that t is equal to the natural log of x. So your answer would end up being 1/2 e to the natural log of x, which you could just write as x, times sine of the natural log of x minus e to the natural log of x, which also you could write as x times cosine of natural log of x. Let's see. Yeah.
Could you just do like integration by parts regularly?
No. You can't. Oh, like you mean for this original thing? Not really. No, I don't think you can.
Is it because sine,
Right. So if I was going to try to attempt to do integration by parts here, just straight off the bat, the only choice I could make for my u would be sine of natural log of x. So if I was trying integration by parts here, and actually this leads me to another question, which I think we should address real quick here. If I was going to directly try to do integration by parts, it might work, but I don't think it's going to be nice, even if it does work. I would let u equal the whole integrand. And then what is dv left to be? Just dx, which does happen in two other kind of well-known intervals. So here, if I find my du is going to be the derivative of sine of natural log of x, which is cosine of natural log of x times the derivative of natural log of x, which is 1 over x dx. And then my v, the antiderivative of 1 is x. This might actually work. I don't actually know because I've never tried doing it this way. So let's see what we get. We write this as u times v minus the integral of v du. We're going to get sine of natural log of x times x. Might work. I would never think to do it this way. Minus the integral of x times cosine of natural x times 1 over x. So you're going to get x times cosine of natural log of x times 1 over x times dx, which then would simplify as x times sine of natural log of x minus the integral of x times 1 over x cancels, and you get cosine of natural log of x. So yeah, you could do it this way. So then you'd have to do the same kind of thing, though. You'd have to do another integration by parts. So then we might as well finish it. Fine, we can do it. So here's what I say. I wouldn't do it this way, even though it's doable this way, because it just feels, I don't know, bizarre is not the right word, but it just feels like not the easiest way for my brain to see it. Probably not the easiest way for your brain to see it either. Maybe that's not true. Maybe this seems really natural to you. I think it makes more sense to do the u sub first and then see an integral that looks more familiar. But we could finish it this way. I could do another integration by parts, let u equal cosine of natural log of x. dv is again dx. du is negative sine of natural log of x times 1 over x times dx. v is x once again. So this whole integral becomes, we have the integral of sine of natural log of x dx equal to x times sine of natural log of x minus all of my uv minus my integral of v du. So it's going to be x times cosine of natural log of x minus the integral of v du. I'm just going to simplify it right off the bat here. So v times du, the x times 1 over x is going to cancel, and I'm just going to get minus, watch, minus sine of natural log of x dx. So then what I have is the integral of sine of natural log of x dx equals x times sine of natural log of x minus x times cosine of natural log of x minus the integral of sine of natural log of x. And then I'm not going to finish it, but you can add this over here. You'll have two of them and then divide both sides by 2, which is the exact same answer that we have up here. Sorry, you can't see it. Just written slightly differently because I didn't write u to the natural log of x as x. I don't know which way feels easier. To me, the first way feels like the typical way people are going to do it, but the second way does work. Kind of cool. Yeah, question. Well, so the reason I'm stopping here, so again, these kind of problems are very kind of special in that the reason I know I should stop is because the integral that I'm getting in my at the end of my integration by parts is the same as the integral I started with. Right? I have the integral of sine of natural log of x and the integral of sine of natural log of x. To me, that means I've kind of repeated myself, and then I can't just keep doing the same thing over and over again because I'm just going to get caught in this loop. But what I can do is I can add that over to the other side and then end this repetition. Let's see, some questions over here. So hopefully you see now where the 1/2 came from in my previous one here. Because if I do this, I'm going to have 2 times this integral, and I'm going to divide both sides by 2. Do we also just do integration by parts twice in this case? I mean, yes. After doing, you said, would we do integration by parts? Yeah. So again, this question is kind of unique in that most times you do integration by parts, you don't get this thing happening where the same integral you start with ends up being something that happens at the end. Usually you just do integration by parts once or twice, and then you eventually get to an integral that you actually can find the antiderivative of. Question.
Do you know if the dollar typically what's much of word problem?
I don't know. All right. So, okay, one more IVP thing, and then we will move to talking about partial fractions. So, one more integral that's kind of special is the integral of the natural log of x. So, similar, excuse me, similar-ish to the problem we just looked at, this does require integration by parts. And just to make sure that everyone's on the same page here, the integral of natural log of x is not 1 over x. The derivative of natural log of x is 1 over x. The antiderivative of natural log of x is, good question, let's find it. So here, some things, even though they don't look like there's multiplication, they technically are. We're going to do integration by parts here, and we're going to let u equal natural log of x, and dv is going to be the leftovers, which is dx. Or du is the derivative of the natural log of x, which is 1 over x dx. And our v is the antiderivative of 1, which is just x. So I want everybody now to write out what this should be equal to. So the integral of natural log of x dx is equal to something times something minus the integral of something. Write it out. Okay, what you should be writing or have written is u times v, so natural log of x times x. I would put the x in front, right? If you write natural log of x times x, it can be really easy to make some mistake like thinking that's natural log of x squared. It's not. The x and the natural log of x are completely separate from each other. Minus the integral of v times du. And then we're going to simplify. I'm going to rewrite this as x times natural log of x because that's the better way to write it. And whenever you're doing this integration by parts kind of process, the whole point is that the new integral should be easier. And x times 1 over x, if you multiply those together, is just 1. And the integral of 1 is about as easy as it gets. The integral of 1 is just x. So there's our answer. The antiderivative of the natural log of x is just x times natural log of x minus x plus c. All right. So let's talk about partial fractions. So yeah. Partial fractions. And we'll start off by exploring the difference between these two integrals. So let's look at the integral of x, gosh, sorry, x plus, not x plus x plus 3 over x squared plus 6x plus 8 dx versus the integral of x plus 1 over x squared plus 6x plus 8 dx. Looking at them, they look pretty similar, but they're going to require wildly different methods of integration. Not wildly different, but different enough. So what I would say is partial fractions is a defined method of integration. I always call it a method of last resort, meaning you should try other stuff before you go to partial fractions, or at least you should recognize that you have to use partial fractions, like nothing else is available to us. Yes. Right, and we have a polynomial in the denominator. So I want to point out partial fractions more specifically are when you have a rational function you're integrating, meaning both the numerator and the denominator have to be polynomials, which just means you have positive integer powers of, actually I should say non-negative integer powers of your variable x. So I've got x to the first and then 3 times x to the 0 if you want to be annoying about it. And the bottom I have x squared plus 6 times x to the first plus 8 times x to the 0. So all my powers of x are non-negative integer values. 0 is technically valid there. So both of these we could, and the other two things have to be true, are the degree on top, meaning the highest power of x has to be strictly less than the degree on the bottom. And finally, the denominator has to be something that factors. So technically, both of these integrals meet the criteria to use partial fractions, because both of these have a denominator that factors as x plus 4 times x plus 2. But in the first one here, I shouldn't use partial fractions because I can do a u substitution. If I let u equal the denominator, my du is going to be 2x plus 6 dx. And if I multiply both sides by 1/2, 1/2 times du is equal to exactly x plus 3 times dx. And I have an x plus 3 times dx. So I should make my life easy and do a u sub if I can. So here, we're going to rewrite this integral as the integral of, well, my x plus 3 dx is going to be my 1/2 du, and my x squared plus 6x plus 8 is just my u. And the integral of a constant divided by u is just going to be that constant times the natural log of the absolute value of u, plus c, and then we substitute back in what u is equal to, and we get 1/2 the natural log of x squared plus 6x plus 8. Let's see. So you should always at least think about, is there an easy u sub here? If I let u equal the denominator, is the derivative of that equal to the top or equal to a multiple of the top? But if it's not exactly a multiple of the top, don't work hard to try and make it work, because it's not going to work. So here, the u sub is not going to work, because we can see that if we pick u equal to the bottom, the du would be x plus 3, and we're just not quite there. And we can't just add on 2 and make it what we want it to be. So here we do have to use partial fractions. So we're going to rewrite our integrand x plus 1 over, and we're going to factor the denominator. The denominator factors as x plus 2 times x plus 4. And I am rewriting the fraction without the integral, because I'm just trying to do some algebra here to simplify my complicated fraction to write it as a sum or difference of two less complicated fractions. Specifically, fractions where the denominators would have this as its common denominator. So I'm going to have something over x plus 2 plus something over x plus 4. And I don't know what those somethings are. So I'm going to write capital A and capital B and try to figure out what they are. I would always recommend doing this by then multiplying both sides of this equation by the common denominator. It's just the easiest way to think about what you're doing. So we multiply both sides of this equation by x plus 2 times x plus 4. The left-hand side, which is the original integral you're starting with, you will always just get the numerator, because the denominators will cancel out. So on the left-hand side, I'm just going to get x plus 1. On the right-hand side, I have to be a little more cautious. When you distribute the x plus 2 times x plus 4 to the first term there, the x plus 2's will cancel, and we'll get a times x plus 4. When I distribute it here, the x plus 4's will cancel, and I'll get b times x plus 2. There's a number of ways of solving the system of equations that we're going to get, but I think the easiest way to figure out what a and b are, well, I should say, the thing you should do first, try and find a and b, are to use what I like to call the convenient values of x. So there are some values of x that are going to make some of these terms equal to 0. Specifically, I'm going to pick x equal to -4. So I plug in -4 for x, well, look what I get. I get -4 plus 1 on the left equal to a times -4 plus 4 is 0, plus b times -4 plus 2 is -2. That makes it really easy to find b. I've got -3 equal to -2b. So b is equal to positive 3/2. And then what should I plug in for x to, what's my other convenient value that I'm going to plug in for x? Right, the thing that makes something else equal to 0. This problem's nice because we don't run out of convenient values. There are other problems where we will run out of convenient values, and then you have to do something else. So here, I'm going to plug in -2 for x. I'm going to get -2 plus 1 equal to a times -2 plus 4 plus b times -2 plus 2. And then I end up getting that -1 equals 2 times a. So a is equal to -1/2. And then the whole point of this is that we can rewrite this integral as the integral of our a value divided by x plus 2 plus our b value divided by x plus 4. So we can say, oh, we're really integrating -1/2 over x plus 2 plus 3/2 over x plus 4. I'm ignoring the -1/2 and the 3/2 really. I'm really just thinking I have a 1 over x plus 2. And the antiderivative of 1 over x plus 2 is the natural log of the absolute value of x plus 2. So what I'm going to get here is -1/2 times the natural log of the absolute value of x plus 2 plus 3/2 times the natural log of the absolute value of x plus 4 plus c. So that is the kind of idea of how partial fractions works. We take this complicated fraction and we write it as the sum of simpler fractions, and then we have to find the constants on top to make it so it's actually equal to each other. So just as a quick aside here, I know that for Dell's exam tomorrow, the sections that are in play are sections 4.6 and then 5.1 through 5.6, and 5.6 is partial fractions. I was planning on talking about section 5.8 as well today, but we probably won't do that because it's not on your exam tomorrow, and I know you want to focus on the exam. And also the other class probably isn't. What is someone else in Temur? Is it Temur Galiava? Is anyone here in her class? Yeah, I was just curious, right? Or no, is it Parlac? I'm sorry, I'm getting the professors mixed up for 2 different classes. Whatever the other class is, I imagine you're not quite up to wherever this is. So I don't think we need to worry about catching up to the other class because I'm sure we're ahead of them. All right, let's do a few more partial fractions problems. 5.7 is not even covered, right? I don't even know what 5.7 is. But definitely if you look, so just so everyone's clear, where I'm getting this information is from, where did I find it? I had it somewhere. It was somewhere. I think there was an announcement for 17B for the Dell. No, yeah. Sorry, 1 second here. Let me get there. Right. So if you look at the announcements for the Dell, there's a midterm 1 announcement posted on Monday. It says the following. It says lots of stuff, but if you scroll down, I believe it said what. Now that I'm looking there, let's see. Yeah, for the midterm, we'll be covering sections 4.6 and 5.1 through 5.6. Please note that section 5.7 will not be included. So there you go. All right. Anyway, I just wanted to point out that we're not going to talk about improper integrals today, even though I want to. All right. So more partial fractions. Where are my examples here? There we go. So, yeah. Let's look at this example here. We'll do two of these. Yeah. Let's say we want to do the integral of 3x minus 8 over x cubed minus 4x squared. So I'll point out this is not going to be a U substitution problem. I'm going to think about letting U equal the denominator, and then we see that the derivative of the denominator is 3x squared minus 8x, and I definitely don't have that. And it's not okay to multiply the top by x, right? So you might say, oh, James, you technically have a multiple of your top, but it has to be a constant multiple, not a variable multiple. So U sub is not on the table here, but I noticed that this does meet the criteria for using partial fractions. The numerator has a lesser degree than the denominator, and the denominator definitely does factor. So we're going to rewrite this as the integral of 3x minus 8, and I'm going to factor the denominator as x squared times x minus 4. And what I would observe here is that I have a repeated linear factor. X squared is really x to the first squared. Or if you want to think about it this way, we don't usually write it this way, but I'm going to do it this one time. You might think about that x squared is really x minus 0 squared times x minus 4. So we have the linear factor x minus 0. It's repeated because it's raised to the second power, and then you have an x minus 4 there. So when we write our partial fraction decomposition, where we write our fraction equal to the sum of lesser fractions, we're going to get not two things, but three things on the right-hand side. So we're going to get a over x squared, and then we need every lesser power of x squared. So we're also going to get a b over x, and then we're going to get a c over x minus 4. And then we're going to do the same thing we did last time. We're going to multiply both sides of this equation by the common denominator that's on the left-hand side. So that we're going to get, we don't love that. Sorry, cool, that's better. All right. So we're going to get on the left 3x minus 8. On the right, a over x squared times x minus 4. You're going to get a times x minus 4. And then b over x times x squared times x minus 4 is going to be b times x minus 4, because one of the x's cancels. And c over x minus 4 times x squared times x minus 4 is going to be c times x squared. And again, I would always use my convenient values before I do anything else. So one of my convenient values of x is what? 4, definitely. The other one, for some reason, is always hard for people to see. The other convenient value of x here is 0. An easy way to identify the convenient values of x, if you look at the original partial fraction decomposition, they're just the values of x that would make these denominators equal to 0. So x equals 4 makes that denominator 0. X equals 0 makes that denominator 0. Yeah.
For A, would you use
No, I would not. So because when I multiply this by this, the x squared cancels the x squared, and I have a times x minus 4.
What is C not C as cubed? Aren't you multiplying it by both?
So I'm multiplying c over x minus 4 times all of this. So when I multiply that by that, the x minus 4 cancels, and I'm left with just c times x squared. Yeah.
Why is the first, like the x squared under the a, why is that squared, whereas under the b it's not?
So the reason why, so here's the thing. If you were thinking about this maybe less carefully, you might not have written that term. You might have said a over x squared plus c over x minus 4 is totally going to work because they have the common denominator that's that. Because you can multiply this by x minus 4 over x minus 4 and this by x squared over x squared. Sorry, you can't really say that. X squared over x squared. But the thing is, that term also is still not going to make my common denominator any different, right? These three things added together still have the same least common denominator of x squared times x minus 4. So if I wanted to add these together, I would multiply this by x minus 4 over x minus 4, and this by x times x minus 4 over x times x minus 4, and this by x squared over x squared. So the thing is, when you have something raised to a power like that, you have to then have every lesser power down to 1 as well.
So if instead, it was like 3x minus 8 all over x squared times x minus 4 squared, then you would have another term and it would also be plus d over x minus 4.
Squared. Right, it doesn't matter which order we write them in. You write the first power first or the thing, right? So yeah, you're right. If that was an x minus 4 squared, you would have a d over x minus 4 squared and then c over x minus 4 to the first. Or let me just go quickly aside here. If someone said, you're trying, we're not gonna actually finish this problem. If someone gave you something awful like 5x squared plus 7x minus 1 over x cubed times x minus 1 to the fourth plus, sorry, times, no pluses, times x plus 2 to the second, the partial fraction decomposition would have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, and it would look like this. It would be equal to a over x cubed, and then we need every lesser power of x. So you'd have a b over x squared, a c over x, and then we'd have a d over x minus 1 to the fourth, and every lesser power of that. So you'd have an e over x minus 1 cubed, plus a c over x minus 1 squared, plus a d over x minus, oh, no, not letters, James, an f over x minus 1 squared, a g over x minus 1, and then finally, you'd have an h over x plus 2 squared, and then every lesser power, an I over x plus 2. That's how your general partial fraction decomposition works if everything is just linear things raised to powers. Yeah.
You did an example in class.
With an x squared plus 1.
Yeah.
We'll get there. We're not there yet. So as long as all your factors are linear, meaning literally x plus or minus something, to include x plus or minus 0, that's a linear factor still. You're just doing this. And the ax plus b thing we'll talk about in a second. So here, I'm still going to use my convenient values. So I plug in 4, I get 12 minus 8 on the left equal to a times 0 plus b times 4 times 0 plus c times 4 squared. That's why I picked 4, because almost everything gets to just multiply by 0 and not be there. So then I have 12 minus 8, which is 4, equal to 16 times c. So 4 over 16 is going to be 1/4 equal to c. And then I'm going to use my other convenient value of 0. So 0 minus 8 is negative 8. On the right-hand side, I have a times 0 minus 4 plus b times 0 plus c times 0. So I end up getting that a is equal to negative 8 divided by negative 4, which is positive 2. Let me just double check one thing here. No, that's fine. Okay, we're good. And then you might notice I've run out of convenient values. There's a couple ways to go about this. Specifically, if you only have one thing left to find, you could make the choice that I don't like, which is just plugging in another value of x. So you plug in like x equal to 1, and then plug in a equal to 2 and c equal to 1/4, and then solve for b. But that's not what I would recommend. What I would recommend is the usual idea of equating coefficients. So normally I wouldn't do all the work I'm about to do, but I'm going to do it here. If you multiply at the right-hand side, I have 3x minus 8 equal to a times x minus 4 times a plus b times x is b times x squared minus b times x times 4 is minus 4bx plus cx squared. And you could combine like terms. So we could say that 3x minus 8 equals, let's say I have b plus c times x squared plus, let's see, a minus 4b times x. And then finally, my constant term is just negative 4a. And then I could use this to find the last value. Yeah, you could technically actually use it to find all a, b, and c. Or you could say, oh, negative 4a has to equal negative 8. So a has to be 2. And then a minus 4b has to be 3. And a being 2 means that b is going to be whatever it is. And b plus c has to be 0. And then we can find the thing. But what I'm going to do instead is I'm going to do this hybrid kind of thing, where first I use my nice values of x. And the way I found the x's was by thinking about what value of x is just going to make things equal to 0. So x equal to 4 was a good choice, and x equal to 0 was a good choice. And then now that I've run out, I'm always going to look at the highest power of x that I have, because it usually has the least things associated with it. So here, if I was actually doing this the fastest way possible, I would say, hey, for x squared, well, on the left-hand side of this equation, I have 0x squared. On the right-hand side of this equation, I have a b times x squared and a c times x squared. So 0 is equal to b plus c, and since I know that c is equal to 1/4, 0 is equal to b plus 1/4, so b equals -1/4. That's how I would really do it instead of writing all this out down here. But I'm getting the same result, right? Down here, if you look, oh, this b plus c here has to equal the 0x squared that I have on the left-hand side. So b plus c has to equal 0. And knowing that c equals 1/4 means b has to equal -1/4. No other option, yeah.
Wait, where'd you get the 0x squared equals bx squared plus cx?
Well, so I'm looking, so I identified that the highest power of x on either side of this equation was x to the what? Right. So I said, I'm going to use that. How much x squared do I have on the left side of this equation? None. 0x squared. How much x squared do I have on the right side of this equation? Well, b times x is a b times x squared, and c times x squared is a c times x squared. So on the right-hand side, I have a bx squared plus a cx squared. And then because the only way polynomials are equal to each other is if corresponding powers of x have the same coefficients, it has to be true that b plus c is equal to 0. We have no choice in the matter. In this, go ahead.
Can you repeat that?
Yeah. So for polynomials to be equal to each other, which we are saying these polynomials are equal to each other, the corresponding powers of x have to have the same coefficient. So since the power of x squared on the left-hand side has a coefficient of 0, the power of x squared on the right-hand side also has to have a coefficient of 0. So the b plus c that is the coefficient of x squared on the right-hand side has to be equal to 0. You could also find the rest of a, b, and c this way. You could say, oh, -4a has to equal the constant term, which is -8. So a has to equal 2. And then a minus 4b has to equal 3. So then knowing that a equals 2, -4b has to equal 1. So b has to equal -1/4. Exactly like we got right there. That's just not the way I would do it because it's slower. So then we've done the partial fraction decomposition, but we're not done. We still have to actually do the integral. Then we go back and say, okay, well, I'm going to rewrite my integral of 3x minus 8 over x squared times x minus 4 dx as the integral of a, which was 2, I believe, right? I think 2 over x squared plus b, which was -1/4 over x plus c, which was +1/4 over x minus 4. Okay, so to solve for b, we disregard the x squared, so it's b plus, yeah, I mean, so I'm just, you can either kind of include them or not. But like here, right, when I was doing it, I said 0x squared equals bx squared plus cx squared. So then 0 equals b plus c. That's what I'm saying. But yeah, we kind of just, we equate the coefficients of x squared. We don't need to include the x squared in our equation. So what I'll say about this integral, whoops, gosh, I keep bumping this thing. Sorry. What I'll say about this integral is if you have a constant over x or x minus 4 or x plus 3, you're going to get that constant times the natural log of the thing. So I know that for these two pieces here, I'm going to leave this part blank here. I'm going to get -1/4 times the natural log of the absolute value of x plus 1/4 times the natural log of the absolute value of x minus 4. But for this part here, it's not a natural log. I don't just have an x to the first and the bottom. So I'm going to think of that as 2 times x to the -2nd. And just use the anti-power rule and get 2 times x to the -1st divided by -1. -1/4 times natural log of the absolute value of x plus 1/4 times natural log of the absolute value of x minus 4. And if you really don't like the way that's written, you could rewrite it as -2 over x minus 1/4 natural log of the absolute value of x plus 1/4 natural log of the absolute value of x minus 4. Quick questions. No, well, hold on one sec. I have some quick questions for you all. So, integral of 1 over x plus 3. Write down your answer. to be the natural log of the absolute value of x plus 3 because the derivative of the natural log of x plus 3 is 1 over x plus 3 times the derivative of x plus 3, which is 1. Right, there's technically a chain rule there, but the thing you multiply by is the derivative of x plus 3, and the derivative of x plus 3 is 1 plus 0. Okay, one more, and then I'll take questions. How about the integral of 1 over 3x plus 4? Think about your answer, write it down, and then think about taking the derivative and see if you get the thing you're trying to take the integral of. Got time, we got enough time. All right, so we should get almost the natural log of the absolute value of 3x plus 4. Except not quite, because if you took the derivative of that, you'd get 1 over 3x plus 4 times. All right, oh, we need to adjust for that. Divide by 3, or multiply by 1/3. So just like lots of other things we've seen, when you're taking the integral of something and x is multiplied by a constant, we almost always end up dividing by that constant. Okay, questions? Oh, let's do that. Sorry. Yeah.
Is it possible, so if these are x squared in the denominator, is it possible to use the natural log of that and adjust it? Or
No, definitely not. You only, so not in this case, but I will point out, because we're about to see it, that it really depends. So like, if you're just gonna say, if I was trying to find the integral of, I'm gonna make it real easy, 2x over x squared plus 1, then the answer is gonna be the natural log of something. Because if we do the u sub here and let u equal x squared plus 1, our du is exactly 2x dx, and this integral becomes the integral of du over u, or you might prefer 1 over u du, which is exactly the natural log of the absolute value of u plus c, which is exactly the natural log of the absolute value of x squared plus 1. Because the derivative of the natural log of x squared plus 1 is 1 over x squared plus 1 times 2x. Oh, that's what we have right there. 1 over x squared plus 1 times 2x. So let me ask you all, I don't want you to do a u sub here. I want you all to make a really, really educated guess about what this integral should be. The integral of 3x squared over x cubed plus 1. Make a smart guess about what you think that integral is. No, for that previous one, the integral would not be the arctangent times 2x. Although I know why you're asking that question. Okay. If you think you got the right answer, mentally take its derivative and see if you get what you think you should get. So I'm going to think my answer is probably the natural log of the absolute value of x cubed plus 1. Because the derivative of that is 1 over x cubed plus 1 times 3x squared. So a general rule of thumb, which people will abuse, is that if you see an integral of a function on the bottom and its derivative on the top, that's always going to end up being the natural log of the absolute value of the bottom function. Sometimes people are going to not actually show the u sub and just do that. Be like, yeah, I got 2x over x squared plus 1. The integral is the natural log of x squared plus 1. And just jump to that. Yeah, but I really want to point out this integral here is not 2x times arctangent of x. It is true, and I know here's where we're going with this. It is certainly true that the integral of 1 over x squared plus 1 is the arctangent of x plus c. And you can throw in any constant you like, right? If it was like the integral of 3 over x squared plus 1, yeah, that's going to be the arctangent of x times 3 plus c. But if you have a variable up there, it changes the whole story. So we can't just multiply, right? It's really, we can't say that this, right? This is not equal to 2x times the integral of 1 over x squared plus 1. which would be 2x times arctangent of x. We can't pull variables out in front of an integral. So then the question was asked, in case this was asked in the chat, that's why I'm addressing it. Like, I know nothing about that. So why are we talking about the integral of 1 over x squared plus 1? Well, because sometimes you have integrals like this. The integral of, do I want to do that one? Yeah, that's cool. Okay. X plus 1 over x times x squared plus 1. So if I'm going to try and do this with, and again, this one's factored all. I probably would have started, actually, I would have, if I was giving you this question, I would have not factored it for you because it's easy enough to factor. I would have started with that and then observed, as usual, it is a rational function. The degree on top is less or less than the degree on the bottom, and the bottom does factor. And that's as much as it factors. X squared plus 1 is not factorable. But I want to address that for just a second, because let me ask you all a question that's going to have an annoying answer. Is x squared minus 7 factorable? No, not nicely, but yes, it is. This factors annoyingly as x minus the square root of 7 times x plus the square root of 7. So the better question that we should actually say, instead of asking if something is factorable, you should ask, does it have zeros or solutions or roots? So the better question here is, does x squared minus 7 equal to 0 have solutions? And the answer to that question is definitely yes, right? We know that the square root of 7 and the negative square root of 7 are solutions to that equation. Versus, does x squared plus 1 equal to 0 have solutions? Have real solutions? And the answer is definitively no. X squared plus 1 is always going to be greater than or equal to 1, whatever you pick for x. So that's what we mean by when something is an irreducible quadratic factor, or that it does, when we say, quote, doesn't factor, what we really mean is there are no solutions to this thing being equal to 0. So that's why x squared plus 1 is called an irreducible quadratic factor. Can't factor any further. Someone asked, how do we know when to use partial fractions compared to use 7 IBP? That's the crux of what makes this hard, right? That's what you have to ask yourself. How do we know? By going through the different things. And so first, if I see a problem like this, I'm first going to ask for U sub. Can I do a U sub? No, I can't. I'm not going to entertain iteration by parts here because it's not a mixture. I don't see a logarithm or an e to the x or a trig function. So I don't even think about iteration by parts, because iteration by parts we really only use if we have a mixture of types of functions. So then I'm kind of only left with partial fractions. Well, we can't use u sub here because there's not a good choice for u. If I were to let u equal the only kind of plausible thing, which is x cubed plus x, my du is going to be 3x squared plus 1, and that does not look like it's going to work out with my numerator there. So I don't want to have to work too hard to try and make a u sub work. Sometimes I will, but not here when I have another method that's going to be better, for lack of a better term. So for this partial fraction decomposition, the x to the first just gets an a over x, but an irreducible quadratic factor, x squared plus 1, doesn't just get a constant on top, it gets a linear term on top. So we get a bx plus c on top. And really the explanation for why we need that is because if you don't have it, it won't work. If you just put a b on top and then try and find a and b, you end up getting the a needing to equal 2 different values to make the equations actually work out right, which is not realistic. It's not the right thing to do. So here, the process is still going to be the same after this. We're going to multiply both sides by the common denominator. I hope I picked one. Let me just double check one thing here. Okay, good. Yes, all right. So multiplying that through, this times that, we're always just going to get the numerator. We get x plus 1. This times that, the x's cancel, and we get a times x squared plus 1. and this times that, the x squared plus 1's cancel, and we get bx plus c times x. And be careful here, I made an error on purpose. I really, really have to put the bx plus c in parentheses. It is absolutely necessary that whatever is multiplying the bx plus c multiplies the entirety of it. Do I have any convenient values of x? 0 is definitely the only convenient value of x here. Why wouldn't we do a over x squared plus b over, I don't have an x squared. I have an x squared plus 1, which is a different thing. So in the previous thing here, right, if you have, so I'm going to go back here for a second. If you have a linear, x minus 1 is linear, right? It's like a line, y equals x minus 1. If you have a linear factor that's repeated, then you need that linear factor to its highest power and every lesser power. But here, my linear factor x to the first is only raised to the first. So the only power I need of it is x to the first. And similarly, my x squared plus 1 to the first isn't repeated. I don't need any higher or lower powers of it. That's the only one I get. Question?
Bx plus c, why don't you just do bx over x plus c?
Because it won't work. Let me show you why. I was hoping someone would ask that question. So let's say we try doing this. X plus 1 over x times x squared plus 1 equal to a over x plus bx. You want to do b or bx?
Yeah.
Okay. What's that? Okay. So if we try this, it's not going to work. So here's what I mean. We're going to multiply both sides of the common denominator. I'm going to get x plus 1 equal to a times x squared plus 1 plus, sorry, I have to actually, I guess I should write out the work I'm doing. Good to write your work out. So a times x squared plus 1, and then the x squared plus 1's cancel, I get b times x times another x. So let's actually just equate coefficients. So here, let's see what I've got. On the left-hand side, I'm going to write it fully. On the left-hand side, I have a 0x squared plus a 1 times x plus a 1. On the right-hand side, I have an a times x squared plus an a times 1 plus a b times x squared. So first of all, these can't equal each other. I don't have an x term on the right-hand side. I'm out of luck, right? They literally cannot be the same because they're both polynomials. They have to have the same powers of x with the same coefficients. And on this side, I have an x squared, I have an a times 1, and I have an x squared. There's no way I can get the 1 times x. Alternatively, you could also point out that if we actually try to equate coefficients, we need that a plus b has to, actually, that's sure. I mean, that's kind of funky. A plus b has to be 0 here, and a also has to be 1. I guess that'll actually be okay here. But the fact that, all right, I still can't get that to come out. It doesn't work. So there's an algebraic proof of why you need to have the bx plus c, which is a little bit complicated, but the real answer is it doesn't work if we don't do it that way. And it has been proven. So sorry, going off the rails here. So back to over here. It's funny, usually people ask it to be b over x plus 1 instead of bx plus c, or bx over x plus 1. So if we pick our convenient value of x equal to 0, we're going to get 0 plus 1 on the left equal to a times 1 squared plus 1 plus b times 1 plus c times 0. So 1 is equal to 2a, so 1/2 is equal to a. And now I've run out of my convenient values of x. So now I am going to go to equating coefficients. So if I start multiplying out the right-hand side, I have x plus 1 equal to a times x squared plus a times 1 plus b times x squared plus c times x. Or rewriting it, on the right-hand side, I have a plus b times x squared plus c times x plus a. On the left-hand side, I have 0x squared plus 1 times x plus 1. So I feel like I've made a mistake somewhere. Yeah, I really feel like I have. Yeah, that's what I'm seeing, right? What did I do wrong? Oh, I did. Thank you. Yeah. So that's why it's good to sometimes look at your work. So this should be 0 plus 1. So A1 is equal to 1 times A. So we really get A equal to 1. Thank you so much. Cool. Question.
Could you explain how you got the x squared or 0x² plus x plus 1 again?
So are you cool with how I have the x plus 1? Well, it's just the same as that, right? X plus 1 is 1 times x plus 1. What I'm doing here on here versus here is I'm writing out all the same powers of x with whatever their coefficients actually are. So this x really is a 1 times x. And I don't have an x squared, but I can write that as having 0 times x squared. Because 0 times x squared is what? 0. So I'm not really changing it. I'm just writing it in a way so that I can say, oh, I know that 0 has to equal a plus b. Right? These two have to be the same. And then I know that 1 has to equal c. So great, c equals 1. And using the correct fact that a equals 1, I can say that 0 equals 1 plus b. So b equals -1. And then I've got all my coefficients. Some people, not me, prefer to just do it this way. And just say, I'm going to get a equal to 1, and then c equal to 1, and then a plus b equal to 0, so b has to equal -1. It's fine in some examples, but sometimes it's really not. So I would always recommend using what I like to call the convenient values of x and then equating coefficients if we need to. But it's a matter of preference. So back to the actual integrating of this thing. That means we can rewrite our integral of x plus 1 over x times x squared plus 1 dx as the integral of, so a was 1, and then b was -1 and c was 1, so it's a -1 times x plus 1 over x squared plus 1. So here's what always will happen when you have an irreducible quadratic factor like x squared plus 1, and you have two things on top like that. You have to break it up. There's no choice. You must rewrite this as the integral of 1 over x plus -x over x squared plus 1 plus 1 over x squared plus 1. There's no other option. Two of these integrals we know. Actually, I would argue all three of these we know, really. So I will point out that usually I wouldn't break this up as 3, but I'm gonna break it up here just so you guys can see it. So I have the integral of 1 over x minus the integral of x over x squared plus 1 plus the integral of 1 over x squared plus 1. Although I wouldn't normally encourage you to write this down, I would just go from here. What's the integral of 1 over x? The natural log of the absolute value of x. And what about the integral of 1 over x squared plus 1? Someone could say something. I think you know it. It's definitely arctangent. And what about the integral of x over x squared plus 1? Well, a minute ago, we did the integral of 2x over x squared plus 1, and we got the natural log of the absolute value of x squared plus 1. So it seems like the natural log of the absolute value of x squared plus 1 would be a pretty good guess, but I'm off just slightly. If we took the derivative of this, we would get 1 over x squared plus 1 times what? But I don't have a 2x, I have just an x. So I can adjust for a constant by multiplying by 1/2. Now, really the work I'm not doing there is I'm not showing the work of doing the u substitution. We could instead say, oh, if we're going to integrate x over x squared plus 1, we could do the longer work of saying, oh, I'm going to let u equal x squared plus 1. my du is 2x times dx, 1/2 du is equal to x dx. And then this all is going to end up giving me that I have the integral of 1/2 du over u, which is then going to be 1/2 natural log of the absolute value of u, which is then going to be 1/2 natural log of the absolute value of x squared plus 1. That's the work I didn't show because you can get away with not showing it sometimes. Somebody asks, how do I know that I had to break the fraction like that? Experience, really, but so I will tell you, it's always the case. You always have to break it up into the constant over x squared plus 1, and the integral that's always going to be that constant times the arctangent of x. And then you have to break it up as the x thing over x squared plus 1, and that's always going to be some constant times the natural log of your denominator. It always plays out that way. So just as a quick example, I got 9 minutes. Yeah, I can make this work. So if, and that's actually, so if you ended up with something like this, let's say we ended up with doing a partial fraction decomposition and the x squared plus 1 part ended up having, say, a 3x plus 5 over x squared plus 1. We have to break it up. So you have to write it as the integral of 3x over x squared plus 1 plus 5 over x squared plus 1. And then I think we can jump straight to the end. We know that this is going to equal 3 times something times the natural log of the absolute value of x squared plus 1 plus 5 times the arctangent of x plus c. And I'm just going to check by taking the derivative of this in my head. The derivative of this is going to be 3 times 1 over x squared plus 1 times 2x. So I need a 1/2 to adjust for the 2 there. But literally for these irreducible quadratic factors, which are usually x squared plus 1, it's always going to work out this way. Always. I'm saying it again, always. I don't actually know what you might get asked. So I'll just point out, if you instead encounter, if you instead encountered something like 2x plus 1 over x squared plus 9, if that was your irreducible quadratic factor instead, which I really hope is not the case, you'd still have to break it up. And then I don't know what the expectations are around your memorization of this, but essentially, if that's a number other than 1 there, I'm seeing that as x squared plus 3 squared. So this part here, that integral is going to be 1/3 the arctangent of x over 3. So more generally, and again, I'm not sure if you're expected to memorize this or not, but the integral of 1 over x squared plus some constant other than 1 squared is 1 divided by that constant times the arctangent of x divided by that constant. And then this first part here would just be the natural log of the absolute value of x squared plus 1. Kind of gross. So if you have one of those x squared plus 9s or x squared plus 1s or some irreducible quadratic factor, you always have to break it up into the 2 pieces on top being separate fractions. Always. Always, always, always. Okay, one more thing, because there is one more thing we need to talk about here. Yeah, and let's make it truly heinous. So let's say that someone gave you something ridiculous like the integral of, let me make sure I copied this down correctly here. 3x to the 4th plus 2x cubed minus 31x squared minus 18x plus 39 divided by x squared minus 9. Let me ask you, do I have a rational function here? I do. Rational just means the top and the bottom are both polynomials. And they both are. The question I think you're answering no to is this rational function proper? Meaning, just like a regular fraction, we say a fraction is improper if the numerator is bigger than or equal to the denominator. This one is improper because the numerator degree is bigger than the denominator. So if I was, so I can't use partial fractions yet because I have an improper rational function. So before I can use partial fractions, I have to do polynomial division, which is kind of gross here. So if we do it, the x squared minus 9 goes into the, yeah. I should actually do, I'm gonna make this, I should say one thing here. I really should have my middle term here. So I should actually really write this as x squared plus 0x. Sorry, that's an x, not an x squared, minus 9. So that when I multiply it out, the things line up nicely. And then it's going into 3x to the fourth plus 2x cubed minus 31x squared minus 18x plus 39. The good news is if you see something terrible like this on a test, it means someone has taken the time to make sure that the division works out nicely. So even though it looks terrible, it's actually a good sign, assuming I didn't make a mistake. So then what do you multiply by x squared to get 3x to the fourth? 3x squared. Multiply by all this, you get 3x to the fourth plus 0x cubed minus 27x squared. Subtract. 3x to the fourth minus 3x to the fourth is 0. 2x cubed minus 0x cubed is 2x cubed. And negative 31x squared minus negative 27x squared is negative 31 plus 27, which is negative 4x squared. Bring down the next term, repeat the process. What do you multiply by x squared to get 2x cubed? 2x. 2x times x squared is 2x cubed. 2x times 0x is 0x squared. And 2x times negative 9 is negative 18x. And that isn't x. I really, sorry, I know I made it look terrible. That's an x. Subtract. That minus that 0. Negative 4 minus 0 is negative 4x squared. And negative 18 minus negative 18 is 0x. Bring down the next term. So then what do you multiply x squared to get negative 4x squared? Negative 4. Negative 4 times x squared is negative 4x squared. Negative 4 times 0x is 0x. And negative 4 times negative 9 is 36. Subtract 30. So that minus that is 0, 0. 39 minus 36 is 3. What that means is we can then rewrite this integral as the quotient 3x squared plus 2x minus 4 plus the remainder divided by the divisor. And then the remaining part here, so most of this is easy, right? That's going to be equal to x cubed plus x squared minus 4x plus the integral of 3 over x squared minus 9. And now this part is where you actually do need partial fractions. So then over here, yeah, I got a minute. Over here, you would say, oh, 3 over x squared minus 9 is really 3 over x minus 3 times x plus 3. Be careful, right? X squared minus 9 is a totally different animal than x squared plus 9. X squared minus 9 definitely factors. X squared plus 9 definitely doesn't. And we write this as a over x minus 3 plus b over x plus 3. It does not matter which order you write the factors in. I'm usually just looking at whichever one I've written first over here. Multiply both sides by the common denominator. We get 3 equal to a times x plus 3 plus b times x minus 3. Plug in x equal, I'll do it. I'm going to do it the other way, even though I normally wouldn't. No, I really don't want to. I'm not going to do it the other way. Plug in x equal to 3. You get 3 equal to a times 6. So a is equal to 1/2. Plug in x equal to negative 3. You get 3 equal to b times negative 6. So b is equal to negative 1/2. And then you're going to end up integrating what? 1/2 over x minus 3 minus 1/2 over x plus 3, which will end up being 1/2 natural log of the absolute value of x minus 3 minus 1/2 natural log of the absolute value of x plus 3. So then that'll be what goes in right there. So now I've not left a lot of room for. So I guess I can write the final answer down here. The final answer would be x cubed plus x squared minus 4x plus 1/2 natural log of x minus 3 minus 1/2 natural log of x plus 3. Okay, I know it's 10:20, but I want to say one more thing real quick because there is one more thing I want you to think about. So I'll point out that you definitely have to do polynomial division if the degree on top is greater than or equal to the degree on the bottom. And the equal part is where people get caught up. So if someone asked you to do the integral of x squared minus 1 over x squared minus 4, you have to do the polynomial division. So we would do x squared minus 1 divided by x squared minus 4. It's a pretty easy polynomial division. 1 times x squared is 1 x squared, so then you multiply, you get that, you subtract, -1 plus 4 is 3. So you can rewrite this as the integral of 1 plus 3 over x squared minus 4. And then this is a partial fraction problem. So don't get caught. If the degree on top and the degree on the bottom are the same, that's a partial fractions problem where you first have to do polynomial division. Unless the degrees are both 1. If you, right, because it's not partial fractions, right? If you do, but you still do, like, if you had x plus 2 over x minus 3, still do polynomial division. It's actually really nice if you do it that way. You could do this with the u sub. Shouldn't do it with the u sub. It's easier with polynomial division here.
So you know, you were breaking it up earlier, like x squared b over x squared.
Uh-huh.
Why can't you do that here?
Do what where? Like
break it up into 2 different fractions.
oh, I totally could. It just is not going to help me.
What
So
is it?
well, I wouldn't say, I would say it helps us when our denominator is x squared plus 1 or x squared plus 9 or some irreducible quadratic factor, because for that one specifically, there is no other way to do it. That's why we have to do it there. You're right. We usually don't break it up, except in that one situation. Here, if I tried to break it up, I'd really just be giving myself like 2 different partial fractions problems to deal with, which is going to make more work for myself. Yeah, it's a good question. All right, I should stop talking because it's 10:22 and there is another class in here. I have office hours over in wherever I am next, C class, and then over in drop-in later today.